Hello there. What's this? Oh, this is the notes. That's ugly. I'm just gonna go through real fast and just kind of generally show you kind of what each of these things is kind of saying. Real quick, force is basically mass times acceleration. It's some mass that's accelerating. I mean, if you have a car that it's just not moving, it's not accelerating, so it's not putting any force on you. If it's got the gas pedal held down, you're going to feel it. SI units of force, that's newtons. If only one force acts on an object, think about it, if you, say, push a marble, it's going to accelerate, it's going to move. If more than one force act on the object, you need to find what's called the resultant force. That's when you add them all together. Friction goes in the opposite direction of whenever something is moving. Tension is when you have a string being pulled. So I'm sure Dr. Christo, sorry, in Poe, has very, very well demonstrated what tension is with his pantomimes. The normal force is going to be perpendicular to any surface, so if you have a book sitting on a table, the normal force is basically what's pushing the book up. The normal force is what's keeping the book from going through the table. And the weight, that's the one that you're most familiar with, it's basically gravity times however much stuff there is in an object. That's what mass is. So it's gravity times mass. Drawing free body diagrams, I kind of went over this. The main thing that I didn't cover is that if you have something at an angle, like, actually the window isn't covering it. Let's see if I can, I can do this. Aha! Magic? No magic. Okay, anyway, well, there's this little thing down here that you can't really see. Yeah, there you go. See this right here? So when you're working on an angled surface like this, since the normal force is going to be perpendicular here, and then the friction force is going to be parallel, and then the applied force is going to be parallel, the only real force that's not along this axis set is the gravitational force. So you're going to turn your whole head, make this the x-axis, this line right here, that diagonal, and then you're going to make the perpendicular line the y-axis. And it just helps with convenience. If you convert both the normal force, the friction force, the applied force, if you convert all of that into regular x and y coordinates, you will still get the same answer as long as you do the math right, because everything is still the same. It's just, I like to think of it as an easier way of doing it. Newton's first law basically says that if something's just like chilling out, it's not going to randomly start like speeding at 100 miles an hour at your face. As long as there's no force that's acting upon it, it's not going to suddenly stop. It's not going to suddenly attack you. It's not going to suddenly start moving. It's going to stay at rest unless you do something to it. The other half of that is saying that if you're out in space in a spaceship and you take a marble and you lightly throw it towards someone at the other end of the spaceship, it's going to keep going along a straight path, and it's going to keep moving at the same speed until you either punch it or kick it or it bounces into something. Because there's no other force acting on it. There's no reason that it would suddenly change speed. There's no reason for it to speed up. There's no reason it would change direction. It's just going to keep doing whatever it's doing. So basically, Newton's first law, the law of inertia, says that an object is going to do an object is just going to keep doing whatever it was doing unless something happens. That's the first law of inertia. Inertia, they say mass is kind of a measure of inertia. Inertia is just kind of how much something is going to resist change. So a good example of this is if you have a fridge and you're trying to push that, it's going to be a lot more difficult to push than, say, a backpack along the floor, because it's more massive. It has more inertia. Inertia, you can't quantize it necessarily. There's no units for inertia, but generally you can say that the more mass something has, the more inertia it has. Okay, Newton's second law. Let's see. Okay, so if an object is acted upon by a net external force, the object accelerates in the direction of the resultant force. So what does all that mean? Basically it means that for example here, if you add up the applied force and the normal force and the force of gravity and the force of friction, if you add all those up, whatever final force you get, well, that's going to be equal to this mass times whatever the final acceleration is. So to say when you add it all up, you get, say it's a 10 kilogram box, and when you add it all up, you get maybe 100 newtons. Well, that means that it's going to be 100 newtons in this direction, obviously, like in the x direction. Well, that just means that, okay, if the force is 100, that's the mass, right here, the mass. So mass is 10, so we get 10 is equal to the acceleration. So it's going to accelerate at 10 meters per second down that ramp. That's what that is. It's Newton's second law, F equals ma. It's one of the most famous laws in physics. I think it should be his first, but that's not my choice. But remember, that's important formulas. The force of something is equal to, or rather a force is equivalent to some mass times some acceleration. Hopefully that makes sense. Next, problem solving tips. I'm going to get more into the different ways of expressing this stuff, but I'm gonna get into solving it. I'm gonna do that kind of stuff. Okay, a 1.2 kilogram wind chime hangs from a string. Compute the tension in the string. Well, think about it. The wind chime is pulling downwards with whatever 1.2 times, well, what's gravity? Remember, it's mass times acceleration. Acceleration would be gravity. 1.2 times 9.8, whatever that is. That's how much the string also has to be pulling upwards, so that way the wind chime doesn't just fall down. Okay, it says determine the normal force and friction. So when it comes to the normal force, all you're paying attention to is the, when it's on a horizontal surface like this especially, all you're paying attention to is the is the y details. So it's 3.6 kilograms, and then that times 9.8 gives us the weight, right? And that's actually being counteracted by the normal force to make sure that the crate doesn't go through the floor. So the normal force is just 3.6 times 9.8, whatever that is. I'm not going to do all the calculations right now. And then the force of friction, well, if it's being pulled at 25, with a force of 25 newtons this way, and it's not accelerating, it's going at a constant velocity, well, then that means that friction has to be also working at 25 newtons this way, right? So, oh, I'm sorry, that's not true, because it could be accelerating. It doesn't specify that it's not accelerating. Friction is just the normal force times some constant. Actually, I'm sorry. What I said the first time was true. Forget what I was about to say. An elevator accelerates upwards, find the tension in the cable. I'm going to leave these to you, kind of, because these are mostly pretty simple. Let me just make sure I'm keeping track of time. A block on a ramp. Okay, so you have to look at gravity, you have to convert that into the normal force, which is that red line, and then the component of gravity in the x direction, which is the applied force, that goes here in the x direction. You could put that also above the ramp. The normal force is going to be acting opposite that red line, and then the friction force is going to be acting opposite the applied force, so it's going to be pointing up the ramp. Remember, the force of friction is just this normal force times some coefficient of friction. If you're pulling something at an angle, well then all you really do is you figure out, okay, how much force are you exerting in the x direction, how much force are you exerting in the y direction, using your sines and cosines, which I hope you understand by now. If not, let me know, I'll make more videos. And you use the y direction force. You see basically how much weight you're taking off of the floor by lifting up the box a little bit, or lifting up the crate a little bit, and then that is going to make the normal force less, right? Because then that means that the floor has to push up less to keep the crate from falling through the floor. So the normal force is going to decrease, and then that normal force times some constant gives us the friction. It says to find out the normal force. If the floor is frictionless, determine the crate's acceleration. So that says that the constant of friction is 0. So, I mean, I think you can understand that. If not, let me know. I'll help you out. Static friction and kinetic friction. Basically, if you have a heavy box sitting on the floor, maybe say of your garage, your static friction is how hard it is to push it and make it move. The kinetic friction is once you've made it move. Kinetic friction is how much force you have to, it's basically how hard it is to keep it moving. This is just basically the force of static friction is equal to the normal force times the constant of static friction. The force of kinetic friction is equal to the normal force times the constant of kinetic friction. So all you have to really remember is that the force of friction is equal to the constant of friction times, which they'll give you in the problem, or they'll ask you to solve for. It's equal to the constant of friction times the normal force. And the normal force you usually have to solve for yourself. Newton's third law, for every action there's an equal and opposite reaction. That just means that probably the best example is if you, say Tony and Alex Orsini are standing at opposite ends of the basketball court, and they both chuck the basketball at each other, and the two balls, they bounce in the middle, and then they bounce back. That's because each ball is exerting a force, an equal and opposite force on the other, so then they're pushing each other away. So here the hand pushes on the wall pushes back to keep the hand from going through the wall. It's kind of like similar to the normal force, but not quite. If a rocket pushes the exhaust gases out of like, say, the back end, well, the exhaust gases are going one way, the rocket goes the other way. So that should kind of make sense. Applying Newton's laws to systems, basically what you do is you figure out what the sum of the forces are, or what the total number of forces are. You figure out what the net acceleration is of the system, and then you apply. This is a stupid way of explaining it. I don't think this slide really helps at all in any way whatsoever. I'm going to do a bunch of examples though, so you're going to see, and hopefully those videos will help. I'm going to do those examples in the next couple of videos. I'll see you then.